Okay, I found this nice report from International Energy Agency, which puts out lots of reports related to carbon drawdowns and energies and other related issues in the context mostly of net zero as well. So this report argues that direct air capture is a key technology for net zero. Remember, we've already said that the technologies that are deployed and exist as of now are not so obviously scalable. But nonetheless, by 2050, if we have to hit the 1.5 degrees C target, we need to hit net zero by 2050. So we need to think about these more seriously. So you can think of this as an optimistic evaluation that DAC can help us get to net zero. So global CO2 capture from biomass and DAC in the net zero scenario. And remember, in general, afforestation, reforestation, BECCS, etc. have their own issues in terms of energy demand, water demand. Of course, wildfires can burn down forests, and BECCS can displace food production, affect food security, and carbon capture sequestration, which goes with bioenergy, is still not scalable. So we are always in this kind of a loop. Nonetheless, in 2020, basically there wasn't much CO2 capture from biomass and DAC. We need to scale that up very rapidly in biomass and DAC, direct air capture, to a few 100 million tons. By 2040, we need to be more than 1,500 million tons, so 1.5 gigatons, over 1.5 gigatons. By 2050, you can see that biomass sequestration needed goes up for net zero scenario, and the DAC, direct air capture, adds on top to reach beyond about 2.4 gigatons CO2 as a whole. Global CO2 capture from DACs, which is direct air capture and sequestration, and direct air capture with use or utilization in the net zero scenario, again in terms of millions of tons of CO2. Nothing in 2020. By 2030, we need to have some DAC with use, but a lot of DAC with storage. By 2040, DAC with use goes up here in this scenario, and DAC with storage has to go up quite a bit to 500 million, over 600 million tons. And 2050, DAC with use and DAC with storage together have to reach about 1 gigaton. Remember that CO2 use is something we discussed elsewhere. It is kind of a displacement. So CO2 is put into products, and then those products are used. So carbon is not completely out of the system. It can be re-released. So one has to worry about exactly what the use involves. For example, if ammonium and CO2 are combined to make urea, which is very useful for agriculture, but urea only keeps the CO2 for days to months. But there are others, polymers and so on, that can keep it for much longer time, and enhanced oil recovery can put it away for decades to centuries, and so on and so forth, that we have discussed elsewhere. We also have to worry about global energy consumption and CO2 capture from direct air capture in the net zero scenario. So here is exajoules, and here is gigatons of CO2 captured. So the 2020 scenario, CO2 captured is very low here, doesn't even measure up on this scale here, but obviously it did use energy. We'll see a table soon on how much CO2 has been captured from 2010 to 2020, but you can see that by 2020 the heat and energy requirements will go up, and of course CO2 captured will go up also, but still kind of small, few million tons, less, about, let's say, 0.1 gigaton. 2040, energy requirements, so heat has gone up, energy required is a little bit there. So a lot of the processes involved in DAC require heat, which we have looked at elsewhere, so we won't go into the details here. CO2 captured goes above half a gigaton or so, and by 2050 we need to ramp up to energy requirements of so much here of together with heat and electricity, it's going to be about 5.8 or so exajoules, which is not small. So obviously the carbon sequestered of almost 1.2 gigatons has to more than compensate for the heat and energy that is required to sequester this with direct air capture. So this is always a battle. What is the cost per ton of direct air capture at this point, and how are the prices dropping and comparing? We will see that in a minute. So what has happened so far? If you look at 2010 to 2021, direct air capture of CO2 global operating capacity in tons of CO2. So numbers are small, not millions, just tons. Okay, 2010, and here we are in 2021. We are at about just about less than 8,000 tons of CO2. So not really on the scales that are needed, what we need to get here for net zero, but in terms of technology readiness level, this tells us that we are heading in the right direction. So we'll look at the technology readiness level in a minute. And just to touch on the details here, this is the solid DAC and the liquid DAC. So this is in solid DAC, air is drawn into the collector where CO2 is captured by a filter. So you produce concentrated CO2 and release air without CO2 at the other end. Once the filter is saturated, the collector is closed and heated to release captured CO2, where you are regenerating very high concentration or almost pure CO2. So CO2 in the coming out of the air here is very low. Basically you can think of that as having no CO2. Of course air only has 0.04%, so that's already an issue as to how efficient we can be. That's where the heat and energy requirements come in. In the liquid DAC, the capture solution reacts with CO2 in air to form a carbonate salt. The salt is separated into small pellets here that are then heated in a calciner to release the CO2 in pure gas form. Okay, the processed pellets are then hydrated in a slaker and recycled back into the capture solution. So there is some recycling here, and you can see also the pellets from the calciner go into the slaker and back into the pellet reactor, and air that's coming in here is basically going through a process of making it CO2 rich, so that the scavenging of the CO2 by liquid catalyst into pellets is made more efficient. Okay, just a detail. So CO2 capture cost at varying CO2 concentrations in 2020. If you want to do direct air capture where the concentration is really low, 0.04%, the capture cost in US dollars per ton of CO2 is in the range of more than $200, and there is always the argument of where this needs to be to make DAC really economically viable, cost effective, and so on. If you capture it at power generation, you drop the cost quite a bit because the concentration is higher, order of magnitude higher. H2 in the steam methane reforming again is got a little bit higher CO2 concentration, so cost drops a little bit. Iron and steel, it's here. In the natural gas processing, concentrations of CO2 are higher, so the cost is lower here. Coal to chemicals, again, fairly high CO2 concentration, so costs keep going down, but eventually you flatten out here for ethylene oxide, for example. So it's intuitive that if the CO2 concentration in the feedstock, which could be air or capture at point sources at industries like power generation, iron and steel, and so on, you will drop the cost per ton in terms of capture cost, but obviously it cannot go to zero even at 100%. So key features of the main carbon dioxide removal approaches and technologies for comparison. You have maturity levels, storage type and permanence, carbon removal potential cumulative to 2100 in gigaton CO2, CO2 capture cost in US dollars per ton of CO2, and water and land requirements. So look at BECS, which we have talked about already in other podcasts. So the large prototype technology readiness level is 6, which is good in terms of its usability as of now. Storage type and permanence is geologically high. Carbon removal potential is here from 1000 to 1170 gigatons cumulative to 2100. CO2 capture cost is at 15 to 80. Water requirement is high and land requirement is medium. Okay, so DAX, on the other hand, technology readiness is similar. Storage type and permanence high. Carbon removal potential is similar, but the capture cost is an order of magnitude higher, or at least quite a bit higher. Water requirement, on the other hand, is low, and land requirement is low. Enhanced weathering minerals, technology readiness is low. Cost is similar, and the water requirement are high, land requirement is low. Land management and biochar production, technology readiness is low. It is got similar carbon removal potential and cost compared to DAC, for example. Water requirement is low and land requirement is medium. Ocean fertilization and alkalization, which we have talked about, technology readiness is low again. So storage types here are high for enhanced enhanced weathering, medium here, and low for afforestation and reforestation. So just gives you a sense that if you think of a portfolio of CDR approaches for net zero by 2050, then DAC fits in very well with all these categories here. And you can add additional details to it in terms of assessment of DAC's direct air capture with storage as a high quality CDR. So additionality, carbon is removed more than what would naturally happen. So evaluation of this additionality performance is very high. So any method you use, amount of CO2 removed has to be much more than when we do nothing. So baseline scenario. Durability is very high. Minimal emissions displacement is medium to high. So carbon removal activity has minimal risk of displacing activities and thus causing further CO2 emissions. If you do storage, then you don't just move CO2 into use in polymers and other things that are then re-released elsewhere after some time. So the displacement evaluation is medium to high. Carbon accounting, carbon removal activity results in net negative carbon emissions to the atmosphere when upstream and downstream emissions are also accounted for. These activities can quantify the carbon that is removed. So evaluation is high. Do no harm, medium to high. So the negative impacts of the solution at large scale should be minimal. So it's not a Frankenstein experiment, that it is actually a real player, a key technology for reaching net zero. So like energies, we need a portfolio of renewables. CDR also needs a portfolio with BECS, afforestation, ocean alkalization, enhanced weathering, and so on. So direct air capture is very much a key technology for reaching net zero. Easy enough to convince ourselves, provided the technology will continue to scale up. Right now we are not there yet, right? This is always a caveat.